This is a really quick lesson on how to manipulate equilibrium expressions and equilibrium constant values if you change around a chemical equation. It's very simple. So at this point you should be able to write a mass action expression if you're given an equation, right? Products raised to whatever the coefficient is over reactants raised to whatever their coefficients are. And also use the mass action expression that you write in order to solve for concentrations or pressures if it's a Kp expression. By the end of this video, you should be able to manipulate a mass action expression and manipulate a K value that you calculate. So the first manipulation we're going to do is if we look at a reaction in reverse. So the first equation that's written here, we write the Kc expression with the products of the forward reaction as the numerator and the reactants as the denominator, and again we raise them to their power. Now the second equation, what we've done here is we've just written it in reverse. So if we write it in reverse, now the substances or the substance in this case that was the reactant in my first equation is now the product and the numerator in my second mass action expression, and the substances that were originally my reactants in the forward reaction are now the products in my first forward reaction are now the reactants in my second reaction and now the denominator. So what we're doing here is we're just taking the reciprocal. So if you reverse a reaction, the manipulation that you do to the K value is you take the reciprocal of it. So reverse reaction, K, new K is reciprocal because you're flipping the equation around. The second manipulation we're going to do is if we multiply a reaction by a certain factor, the new equilibrium expression is raised to that factor as a exponent, as a power. So again, we're looking at the same original equation we looked at last time. So the original Kc expression, we have products over reactants. And now what we've done here is we've just taken these coefficients and we've divided them all by 2. So the factor that we've multiplied them by is 1/2. So our new Kc value is going to be raised to the 1/2 power. Or you're just, in other words, you're just taking the square root of it. If you were to double the coefficients, the Kc would now be this, and when you calculate it, it would be raised to the second power, or you'd square it. So the factor that you use to multiply the reaction by, it now becomes the new powers of the exponents. Another manipulation we can do is adding equations together. So this is kind of like another extension of Hess's law. So we have two equations that should be shifted over a little bit there, and we have each of their K values. So the equilibrium constant for the first equation is 2, the equilibrium constant for the second equation is 3. When we combine those equations and add them together to get an overall equation, we find the product of the K values. So when adding equations, you multiply the K values. Now, you could be asked to do a combination of any of these things, and some of the homework problems have that. You might be asked to, do the reverse reaction and then double the coefficients. What would that do to K? What I would recommend that you do in those cases when it's multiple manipulations in one problem is do each step independently. Find, if it's reversed, find the reciprocal of K first. Then if all the coefficients are multiplied by 2, take that answer and square it. I feel that it would be to your advantage to do it in multiple steps, so you have less of a chance of screwing it up. A couple other vocabulary words. This is kind of related to the earlier lessons about just writing K expressions at first. If you have a system that's considered to be in homogeneous equilibrium, that would just, I mean, looking at the prefix homo means the same, means that all the substances involved are in the same phase, so either all gases or all aqueous. And we could easily write the K expressions for any of these. We could write Kc or Kp. So if we wrote K, let's do Kp for the first one since they're all gases. Again, you would be told to write Kp. So it'd be pressure of NH3 squared over pressure of nitrogen times pressure of hydrogen to the third power. And then if we wrote, we can't write a Kp expression for the second equation because they're not gases. So we'd have to use Kc. This would be hydrogen times the cyanide over the HCN, and all those have coefficients of 1. So those are all homogeneous equilibria. Another type of equilibrium system is heterogeneous, which you could probably assume there, that involve more than one phase. We can still write equilibrium expressions for these. We just have to make sure that the only substances included in the equilibrium expression are gases and aqueous solutions. Only gas or aqueous, which was mentioned in an earlier lesson. So no solids, no liquids. So the first one, the K expression, would, since we don't put solids in, would just be concentration of oxygen cubed. And the K expression for the second one would be H2 squared times O2. If there were no gas or aqueous products and they were only on the reactant side, you would have to put a 1. It would be a 1 on top for your numerator, and all of your reactants would go on the bottom. So in summary, by this point you should easily be able to write an equilibrium constant expression, either using a Kc or a Kp depending on what it tells you to do. You should be able to tell what happens to a value for an equilibrium constant if you change the coefficients in the equation. So if you double the coefficients, your K value is squared. If you cut it in half, your K value is now going to be the square root. If you multiplied it by 3, the K value would be cubed, etc. If you're finding K for a summary equation, if you're given the component equations and asked to find the K for the summary, you would multiply the equilibrium constant values. Let's see, tell how K depends on the way equilibrium concentrations are expressed. Oh, so if you're told, if it mentions pressures, equilibrium pressures in a question, then you would have to write a Kp expression. If it doesn't designate anything, generally Kc is fine. And then you should also be able to explain what K is telling you about a reaction. That if K is greater than 1, then when the system's at equilibrium, there will be mostly products. If K is less than 1, it would be mostly reactants. And if K is equal to 1 at equilibrium, you would generally have equal concentrations of reactants and products. The next lesson will be introducing some more complex problem-solving methods that are essential for the rest of our equilibrium studies in this course.